So our goal is to understand two-dimensional linear systems, which are the following type of differential equations. So we have our goal is to find x and y. So we're trying to find a pair, x a function of t and y is a function of t. So that makes it a 2D system. And what makes this system a linear system is the fact that when we look at the differential equations are linear in x and y, right? So a two-dimensional linear system as opposed to a nonlinear system is two first-order differential equations of this form, where x dot is a constant a times x plus a constant b times y, and y dot is a constant c times x plus a constant d times y. So we're going to extract this in the following notation. We're going to have capital X dot is some matrix A times X, where the matrix A is A, B, C, and D. So we're going to think about this way, and we're going to think about this X as, that means XY, essentially. Okay. Now, for any linear system, the origin is the fixed point, right? Because obviously, if I stick in x equals 0, y equals 0, I get x dot is 0 and y dot is 0. So the origin is the location of the fixed point in the linear system. So the game is not to find the fixed point. The game is to characterize the flow near the origin, or near the fixed point. All right, so the origin is going to be our fixed point, and our goal is to characterize what the flow can look like near the origin under different values of A, B, C, and D. So A, B, C, and D are just constants at this point. And it turns out that I can have different values of these variables and get different types of motion. So for instance, our favorite is the simple harmonic oscillator. So mx dot plus kx is equal to 0. We can convert this by saying that the velocity is equal to x dot. So we have x dot is equal to v, and v dot is minus k over mx, which I'm going to write as minus omega squared x. So now if I think about this as a linear system, I have x dot is equal to 0x plus v plus 1 times v, and v dot is minus omega squared x plus 0 times v. So there's my linear system. And the solution in phase space to the harmonic oscillator, we know, is just closed orbits. And there's a fixed point here in the middle, right? So the origin is a fixed point, but we know that these are just closed orbits. Yep, you two good?
Yep, good.
So just to use words, the phase portrait is the picture of the flow. So I've drawn the phase portrait, and any point in the flow is a phase point, which is a particularly interesting word, but okay, fine. So that's the point of the flow. Okay, so now what we're going to do is an example which might look a little bit easy at first, but we're going to pull out a bunch of different possibilities. So again, we're working with x dot is ax because it's a linear system. And we're going to let the matrix A be A, 0, 0, minus 1. So x dot, this is going to look like a really easy looking system, but we're going to be able to see that there's a lot of different motions that we can get out of the system. So right now we have just one parameter. There's only one parameter in this system. It's the letter A, right? It can be any different numbers. And these two equations are already uncoupled. So if I solve them, I would have x as a function of t is x0 e to the at, and y as a function of t is y0 e to the minus t, right? So these are my solutions to my system. Okay. But now I want to think about what the phase portrait might be at different values of the parameter A. Okay, so let's suppose that A is less than -1. Okay, if A is less than -1, then the rate at which the x value is going to 0 is faster than the rate at which y is going to 0. See, so let me just pick a value. So let me suppose that a is -5. Then my equations are x is x0 e to the minus 5t, y is y0 e to the minus t. Okay, so if a is -5, that's a number smaller than -1, then the x values are going to go to 0 faster than the y values are going to go to 0. And so when I go to draw the phase portrait, the origin here is a fixed point. So this is the x-axis, this is the y-axis. I'm going to come down the y-axis. So the y-axis is x equals 0. Right, so the y-axis is where x is equal to 0, and the x-axis is where y is equal to 0. So I'm going to, if I start off on the y-axis, I'm just going to come straight down. If I start off on the x-axis, I'm just going to come straight into the origin. Okay, that makes sense? But now if I start off at a point up here, I got to go to the origin. This point is the phase flow is going to drive me to the origin. But the phase flow is going to drive me to an origin such that I get closer to x equals 0 faster than I get closer to y equals 0. So I'm going to come into the origin this way. See, I'm moving left is making x go to 0. Moving down is making y to go to 0. Because x is e to the minus 5t, I move left faster than I move down. So for this particular flow, the flow is in towards the origin. Oh, no, that's wrong. But it's coming in more this way. That sort of makes sense?
Yeah, that makes sense.
Now, if a is equal to -1, then x is x0 e to the minus t, and y is y0 e to the minus t. And so now, again, the origin's a fixed point. Again, I would be coming in along the x and y axes, But now the rate at which I'm coming towards the origin is the same in both the X and Y directions. And so I'm going to come in evenly in all directions. All right, so that's fine. Now, what happens if A is between -1 and 0? So let me suppose that A is 0.5 or negative 0.5. Then x0 or x is now x0 e to the minus 0.5 t, and y is y0 e to the minus t. So now I approach y equals 0 quicker than x equals 0. The rate at which I'm going to get to x equals 0, I'm going to get to y equals 0 as t goes to infinity, but I'm coming in along a different direction. So again, the origin's a fixed point, but now I'm going to come in this way. That makes sense? So that's as opposed to when A was less than -1, I'm coming in along the other axis. Okay. All right, what do you get if A is equal to 0? Now, x was supposed to be x0 e to the at, right? So what happens if A is equal to 0? What happens to the x coordinate? What's that?
It's just going to be fixed. X is equal to 0. Well, 1, because e to the at, e to the 0 is 1. So x is equal to x naught.
That's right. So if I start right here, what happens to me?
The x component just stays there.
It just comes down. And so it's true that the origin is still a fixed point, but the origin is not the only fixed point of this flow. Now the entire x-axis are fixed points. See, I have this sort of weird degeneracy, right? So when A is exactly 0, not only is the origin a fixed point, every point along the x-axis is a fixed point. Okay. And now, if A is positive, though, I get something qualitatively different. So now I have a positive number here. So let's suppose that A is +6. Then I would have x is x0 e to the 6t. So if I'm at this point here, if I start off at this phase point, somewhere along the x-axis, I've got a positive exponential. And so I'm actually going out along the x-axis, and I'm going out along the minus x-axis. I'm still coming straight down towards the origin in those directions. And so the origin is still a fixed point, but its behavior is different. The points around the origin, the behavior is different than it was before. So now, if I start out up here, I'm going to swoop out and go that way. Okay.
Reminds me of algebra 2.
Okay.
Yeah, because you had like these hyperbolic like.
Yeah. So I mean, this is the curve is going to be somewhat hyperbolic. 1 second here. Hold on a minute.
Michael, are you in my quantum class?
Yeah, believe so.
Okay. So these different things have different names. So let me go back up here. Okay. This particular shape to the phase portrait is called a stable node. So a stable node is the fixed point here. I'm coming towards the fixed point in all directions. Okay, so we say that X star, the origin, is a stable node. This particular phase portrait here is called a star. Sometimes it's called a symmetrical node. Okay. This one is also a stable node. This is called a line of fixed points for not creative reasons, because it's a line of fixed points. And this one here is called a saddle. Okay. And so the origin here is called a saddle point. If you think about a saddle, like a horse saddle, right? The point in the middle of the saddle, you run away in one direction and you run towards in the other direction. You understand what I mean by that, right? So
The Pringles chip.
like Pringle chip, right? I run towards it in this direction and away into those other directions.
So is it a quasi-stable fixed point or a semi-stable, or is it?
No,
You are
but we
running
want
away.
to call it. We're going to call it a saddle.
Okay.
Okay, but you're on to something. There are directions here which are different, right? So there's an important piece of information here in the saddle. We're going to define two manifolds.
Manifolds.
Yeah, okay.
Manifold.
So what do we mean by manifold? A manifold is a collection of points with some other properties, but so the first manifold that we're going to define is called the stable manifold. The stable manifold is going to consist of all the points such that as t goes to plus infinity, the points run to the origin or the fixed point. So the stable manifold is the collection of all the points that as you run towards t equals infinity, run into the fixed point. And so that's the y-axis.
That's the
y-axis is the stable manifold.
That's what I had been looking at. Okay.
Okay. And then we're going to define also the unstable manifold.
Just curious, could we then call the stable manifold a set that includes the points along the y that are converging?
Yeah, so a manifold is a set of points. It's a collection of points. Okay, the unstable manifold is that are defined as t goes to minus infinity let me write it better. So the x-axis here represents the unstable manifold. It is all the points that if you run backwards in time, end up in the fixed point. Okay. So you can have a stable manifold, you can have the unstable manifold. Now, if we go back up to our saddles that we've drawn, the stable node, this stable node, the entire plane is the stable manifold. Right? Because all the points go to the fixed point as I run forwards in time, and there is no unstable manifold. Right? But if you have a saddle has two sets of points, one that is part of the stable manifold, one that's part of the unstable manifold, and then other points are part of neither, right? So a point that's up here, right? So this phase point up here is on neither the stable manifold nor the unstable manifold. If I run it forwards in time, it runs out here to infinity. If I run it backwards in time, it runs to some other place at infinity. Okay, so the stable and unstable manifolds are very important because they divide portions of the phase portrait. So when we go to nonlinear flows in 2 dimensions, we'll see that things can begin to join up. Okay.
So as far as like, so you can have multiple manifolds that collectively encompass or make a geometry. Is that
Yeah, so
kind of
you might have a nonlinear flow. For instance, that has maybe a saddle here. And so maybe I'm going this way. And then maybe over here, I have a stable node. So maybe these points flow into here, and these points flow into here, and these points might flow into here, and these points might flow into here. And so locally, in this blue box, this particular fixed point is behaving like a saddle. And the stable manifold, part of the stable manifold of this particular fixed point, part of the unstable manifold of this fixed point is becoming this part of the stable manifold of the next one next to it. Right? And then there might be over here, we might have a limit cycle. So we might have something that's spiraling out, and this might be going around. And over here, these might come down onto it. And then over here, these might come out over this way. But the key thing to understand is that the stable and unstable manifolds in nonlinear flows divide up the space. So one of the things about 2D flows is that the paths can't cross each other. And that's because of the existence and uniqueness theorems of differential equations. So because your differential equation has to have a unique solution, You can't be at one place and go in two different velocities at the same time. So the paths can't cross each other. So once you establish your stable and unstable manifolds, you can't get past those regions. Those regions block off different sections of the graph. Okay, so you can have a bunch of different features, but they get nicely contained by the stable and unstable manifolds. Okay. All right, so now
Very cool.
stability language. There are some words that we need to define. Okay, so a fixed point is attracting if all the trajectories that start near X star approach X star as t goes to infinity, right? So in our stable node examples, these fixed points are attracting because any phase point that I pick near that stable node approaches the origin as time goes to infinity, right? So that I would say that those are attracting. Okay.
As objects, what is attracting? What sort of objects?
The
What sort of-
fixed point is said to be attracting.
Okay.
We say that the fixed point is attracting if the trajectories that start near it approach it as t goes to infinity. If all the trajectories approach X star as t goes to infinity, we say the fixed point is globally attracting. In other words, if our stable nodes that we have up here, this stable node is globally attracting. Every phase point eventually ends up in that node. Okay. On the other hand, in my nonlinear flow, I would say that this fixed point, let me label this fixed point A. The fixed point A is attracting because any trajectory that starts that is near it goes towards it, but it is not globally attracting.
Can we say it's locally attracting?
Yeah, it's just attracting, right? It's not globally attracting. It influences its local neighborhood, but not its global neighborhood. Okay. Now, if all the trajectories that start near X star stay near X star for all time, then we say that X star is Lyapunov stable.
Interesting word.
Okay, so Lyapunov, Russian mathematician. So we're saying that if all the trajectories that start near the fixed point stay near the fixed point for all time, then the fixed point is Lyapunov stable. Now, let's suppose that you have a flow like our harmonic oscillator flow. Right, suppose this is X and Y, and this is my flow. I would say that this flow let's say that the fixed point at the origin here is Lyapunov stable, but it is not attracting. In other words, if I pick a point, over here, this phase point stays, the trajectory of that phase point stays near the fixed point, but is not attracted to it. So this phase portrait is Lyapunov stable, but not attracting. Okay, so it's possible to be attracting, it's possible to be Lyapunov stable, but then of course it's possible to be both. If a fixed point is both Lyapunov stable and attracting, it is called asymptotically stable. Or just stable. Right? So if you are, so for instance, I would say that this fixed point over here on the right is stable in the nonlinear flow. So the point A as a fixed point is a stable fixed point. It is Lyapunov, it is not globally attracting, but it is Lyapunov stable, and it is attracting. Therefore, it is stable. It is a stable fixed point of the flow. Okay, so the stability language is important in understanding these sort of flows. How are we doing? Just making sense?
Yeah, I'm following.
Okay. All right, now. All right, so if we have x vector dot is a x vector, where A is a matrix A, B, C, D, and we assume that x vector is e to the lambda t times v, where v is constant, where v is some constant vector. So we say, let's assume that there is an eigenvector, that there's some vector here, and it's going to turn out to be an eigenvector, and these lambdas are going to turn out to be the eigenvalues. Let me assume that this is a solution. Then let me see what happens if I make that assumption, right? So if I assume a solution of the form e to the lambda t times some constant vector, so all the time dependence is in this e to the lambda t business, then x vector dot would be lambda e to the lambda t v. Right, so x vector dot, I'd have to take take the time derivative, and so all that can happen is the lambda comes down. But I know that x vector dot is supposed to be a times x. So if I then set these two things equal to each other, I have lambda e to the lambda t v is equal to a e to the lambda t v. And so now e to the lambda t is a common numerical factor on both sides. And so I have a times v is lambda times v, which is my classic eigenvector eigenvalue problem.
Yeah.
Now, you guys are both in quantum this semester, but you may or may not have gotten to this, or if you've had linear algebra, you may or may not have gotten to the classic eigenvector eigenvalue problem. Have you gotten to the classic eigenvector eigenvalue problem before?
I
think once or twice in
Okay,
modern.
so an eigenvector eigenvalue problem is the desire to find the vectors v and the eigenvalues lambda that satisfy this equation. Okay.
You just make it homogeneous minus from both sides, and
Yeah, so I'm gonna do that in a minute. So I'm gonna rewrite this equation as A minus the identity matrix times lambda times V is equal to 0. So I can move the so this I is now the identity matrix. Okay. Now, the key thing to understand in the eigenvector eigenvalue problem is that this would represent two linear equations. Okay. For the components of V, right? So V might be V1, V2. And those two linear equations must be they have to have the same content. They have to be not underdetermined, I guess would be one way of saying it. Right. So basically, in ordinary old linear algebra, let's sort of back up here for a second. In ordinary linear algebra, the goal is to solve m times v is equal to b, right? So the goal is to solve an equation that looks like this, right? Where m is some matrix and v is a vector that you're trying to find. So m here, m and b are known. And so the way we do this is we say that there's some matrix M inverse, and that if we multiply by M gives us the identity matrix. And so the way we solve this equation is we say that M inverse times M times V is equal to M inverse times B. Therefore, V is equal to M inverse times B. Okay, so in ordinary old linear algebra, I have a matrix times my V is equal to B, and I find the inverse matrix, and this, then I can have this game. And now, but to have an inverse,
the determinant can't
the
be zero.
determinant of M cannot be 0. So in order for M as a matrix to have an inverse, then its determinant cannot be 0. Now, the eigenvalue problem, though, is different. In the eigenvalue problem, instead of having a B over here, I have a 0 over here on the right-hand side. And so if the matrix that was in front of V has an inverse, then the only solution is V is equal to 0. So let me write this as some matrix times V is equal to 0. So if M inverse exists, then V is equal to 0, which is Dullsville. Right? Because if M inverse exists, then I would multiply both sides by M inverse, but M inverse times 0 is just 0, and so V is equal to 0. And so that's not interesting at all. So what you want to solve for in an eigenvalue problem is where the matrix in front of the eigenvector does not have an inverse. So in an eigenvector eigenvalue problem, we require that the determinant of A minus I lambda is equal to 0. So it can have no inverse. Because if it has an inverse, then the eigenvector is trivially 0. So see, in ordinary linear algebra, you want the determinant of the matrix to not be 0 so you can invert the matrix. But in an eigenvalue problem, you don't want to invert the matrix, so you require that the determinant of this thing is equal to 0.
If there are only trivial zeros, then the columns are linearly independent.
Then the columns are linearly independent. That's right. So the two equations here, when I said that it's underdetermined, another way of saying this is that these two equations are linearly dependent. They do not carry linearly independent information. The system is underdetermined. Okay, so now my matrix A was A, B, C, D. I've done A minus I lambda is therefore A minus lambda, B, C, D minus lambda. And the condition that I'm interested in is that the determinant of that matrix is equal to 0. I want that determinant to be equal to 0. Okay. And so you can work it out, right? That would be A minus lambda times D minus lambda minus BC is equal to 0. Michael and Weber, you guys both know how to take 2 by 2 determinants.
Mm-hmm.
Yep.
Multiply, subtract. You know how to take the trace?
What do you mean the trace?
Okay, you don't know the trace.
You might
Definitely
call it
don't know that.
You might call it something else, and I don't know if you explain.
No. The trace is the trace. Okay, so the determinant of this is AD minus BC, and I'm going to call that with the symbol delta. Okay, so the determinant of my matrix A, I'm going to call delta. Right? The trace of A is A plus D, and we're going to call that tau. The trace means add up the numbers on the diagonal. Okay. You can show that the determinant of A minus I lambda turns out to be lambda squared minus the trace times lambda plus the determinant of A. So this works in 2 by 2. This does not work in 3 by 3. Okay, so for a 2 by 2 matrix, the determinant of A minus I lambda works out to be lambda squared minus the trace times lambda plus the determinant is equal to 0. And so that tells you that the eigenvalues are the trace plus or minus the square root of the trace squared minus 4 times the determinant over 2. So in a 2 by 2 linear system, the trace is just the sum of diagonal elements, and the determinant is just this minus that, multiply minus the other thing. Okay. And then once you have your two eigenvector values, you go back and find your eigenvectors. All right, everybody good?
Yep.
Now, if,
I like that hack.
yeah, but it's a nice one. So let's suppose that you do one of these problems and you find out that lambda 1 is +6. And that corresponds to eigenvector V1, right? There's going to be two eigenvalues, there's going to be two eigenvectors. And V1 corresponds to 1, the vector 1, 1. Then what that means is that there's a line here with slope of 1, okay, because the x and y, the runs are the same, and that direction is a unstable manifold. Okay. If an eigenvalue is real and negative, the line determined by the eigenvector will be a stable manifold. So let's suppose that lambda 2 works out to be -4. And the vector associated with that is, say, -1, 1. Then that would mean that there's a line this way that is corresponding to a stable manifold. So this is the eigendirection for V2. And then here I had the eigendirection for V1. And so this particular linear system corresponding to the numbers I picked would have a flow that looks like that. That would be my flow for that particular system. Okay. But now let's go back to our formula for the eigenvalues. The trace plus or minus the square root trace squared minus 4 delta over 2. So now the trace squared minus 4 delta, what happens if that is 0 or less than 0, right? If the trace squared minus 4 delta is less than 0, then the eigenvalues are complex numbers.
That's interesting. We didn't do complex.
And the eigenvectors are complex numbers.
Would you then, on this phase diagram, would you only graph, or yeah, would you only graph the real part?
Nope.
Would you just need a completely different graph since you have now your next?
And these will end up being spirals. Right? So if your trace is negative and the eigenvalue is complex, then what you'll get is an inflowing spiral. The trace value here, if you go back and you think about this as x is e to the lambda t times v, if the lambda is and now I'm saying that lambda is working out to be trace over 2 plus or minus the square root of trace squared minus 4 delta over 2. So now, if I have a complex lambda, the complex lambda part has come from this square root that's out here. So it's this trace, it's the sine of the trace, which is giving the real part of the exponential up here. And if that, so if I have this thing and it's e to the minus 3t plus 4it, so let's suppose that I have that. This minus 3t will lead to an end spiral of the flow. The complex part will lead to me going around. Let's go back and do the simple harmonic oscillator. So let's suppose I have x double dot plus x is equal to 0. So let's suppose I had this is my simple harmonic oscillator. So that means I introduce v to be x dot. And so v dot is minus x. So my equations are x dot is v dot is minus x. Or if I write these another way, my equations are x dot is 0x plus 1v. V dot is minus 1x plus 0v. Okay, both good on that? So that means the matrix A is 0, 1, minus 1, 0. Okay. Now the trace of A is 0. That's adding up the diagonals.
Is v dot just an arbitrary choice of? Yeah.
So if I have a second order differential equation, the way I turn it into two first order differential equations is I introduce a velocity. I say that v is x dot. So if I go back over here, this x double dot is equal to v dot. So v dot plus x is equal to 0, or v dot is minus x.
All right, so you're just making substitution to reduce the differential equation, the order.
Yep. And the determinant is plus 1 because it's 0 times 0 minus 1 times minus 1. Everybody good with that? And now my eigenvalues, trace over 2 plus or minus a half the square root of trace squared minus 4 delta. My eigenvalues would be 0 plus or minus the square root of 0, well, there's a half out front, minus 4 times 1. My eigenvalues are plus or minus I. Okay. So pure imaginary eigenvalues make phase flows that are simple harmonic oscillators. So the simple harmonic oscillator is such that it has pure imaginary eigenvalues in its, when I treat it like a 2D linear system.
Because e to the real part will give me the decaying.
It gives you the decay or the expansion.
Yeah.
Okay. And so now if my lambda plus or minus is the trace over 2 plus or minus a half the square root of trace squared minus 4 delta. So now this is why if the trace is positive and lambda is complex, then what you're going to get is an unstable spiral. If you have pure imaginary eigenvalues, you get what's called a center. This particular phase portrait is called a center. And then you could have stable and unstable spirals. Okay, now there's going to be some we should do a bunch of examples with these where we solve them. We'll do that next week. But I wanted to just draw a general graph. So it turns out that if you plot trace versus delta, so this is the trace of A, and delta is the determinant of A. And this is for x vector dot is AX vector. That anything with delta negative, everything over here is a saddle. In other words, if you compute the determinant of A, you're guaranteed to get a saddle, and you get delta's negative, you have a saddle everywhere over there. There's a curve here, tau squared minus 4 delta equals 0. So that's the curve, tau squared minus 4 delta is equal to 0. Inside, okay, so now if tau is positive, what you have up here are unstable nodes. What you have in here is unstable spirals. What you have right along this line are centers, simple harmonic oscillators. So if tau is equal to 0, then you get a simple harmonic oscillator. What you have down here are stable spirals. And out here you have stable nodes. See, because down below, so anywhere where tau is negative, you end up with a stable situation, things flowing towards the origin. Anywhere where tau is positive, you have an unstable situation where you're flowing away from the origin. Okay. And then these lines, this line here, these work out to be stars and degenerate nodes. You have to do a little work to figure out exactly what those are. And then this line here are non-isolated fixed points. At delta equals 0. So if your determinant is 0, you have non-isolated fixed points. Otherwise, you have unstable nodes, unstable spirals, stable spirals, and stable nodes, and centers down the center. So just by quickly computing the trace and determinant of your 2x2 matrix, you know immediately what the phase portrait is going to be, right? I mean, these are just 2x2 matrices, so it's easy to compute the trace, it's easy to compute the delta. So you might not know exactly, so if it's a stable node, you might not know exactly which way the axes are going to go, but you know what the phase portrait is basically going to look like. Okay. So you can characterize a 2x2 system simply by looking at the trace and determinant of the system. Okay. So what we should probably do next week is a bunch of examples. I'll stick up some homework where you actually go through the process and get the eigenvalues, get the eigenvectors, draw the phase portrait, understand what it means. Then we should go and do the very fun Romeo and Juliet scenarios. So one of the funnier things in Strogat's books are you let R be equal to Romeo's love for Juliet. And you let J be Juliet's love for Romeo. Right? Where RJ positive is love and RJ negative is hate. And you write down characteristic situations. So for instance, let's suppose that Romeo responds positively to Juliet's affection. So if Juliet loves Romeo, or Romeo loves Juliet more, But let's suppose that Juliet responds negatively to Romeo's affection and positively to her own affection. So Juliet is, of course, more complicated. So if Romeo loves Juliet, so R is positive, Juliet gets cold feet, J dot is negative. See, if we look so far just at that much, right? If R is positive, then J dot is negative. So Juliet's love is going to decrease for Romeo. On the other hand, if Romeo dislikes Juliet and R is negative, then Juliet kind of warms up. So in other words, she's out of sync with her lover, but then maybe she's in sync with herself. She has a strong feedback to herself. So now Juliet, if she loves Romeo, she goes, yes, I really love him. Or she hates Romeo, then she goes, no, I really hate you. Then you can like evaluate what will happen to their relationship.
Forget about counseling. Model this mathematically.
So you can go through all sorts of different relationship things, which is kind of a fun thing to do. Okay, so anyway, I'm gonna